y. And initial conditions are given. And we use this convention. Xn is nothing but just x0 plus n times h. Yn is the value of y at xn. Fn is the value of f at xn and yn. So these are all used to simplify the notation, simplify the expression. And Euler's method is nothing but the definition of the derivative, right? Yn plus 1 minus yn divided by h equals the derivative. And derivative is nothing but the right side, and right side value calculated is written here. Do you follow me? This is Euler's method. And we can consider higher order method. If we stop at this point, it is first order, right? But if we continue and attach these things, then it is rth order method. For instance, first order method, second order method, and third order, and so on, up to rth order method. So Pauli did the modification. Instead of just multiplying by fn, he averaged fn and f of the next value, average, right? So average of this value is used instead of just fn. This is Hoy's, and people studied it further, and Rangakara developed fourth order accuracy method, and it requires 4 different heights and weight sum, right? Weight sum, such as 1, 2, 2, right? And then 1. So total 6 slopes are added and then divided by 6. So weight average is used. This is a Rangakara, and this degree is fourth order. It has fourth order accuracy. And by using the same idea, we can handle the system of this pattern. Instead of just function of one differential equation, finding just one equation, finding the functions of many equations. Then what we do is we develop the 2 different sets of heights, right? 2 different sets of heights. One for f part, right? This part. The other for this part, right? G part or y part. And then we use these things, but the order is very important. We should not calculate k first and then L. No, we should calculate k1 and then L1. Why? Because, as you can see, when you calculate k2, L1 value is necessary. So if we just calculate k part first and then continue to calculate L part, then we don't know L value, right? Because we don't know L value and unknown value is plugged in, this result is unreliable. Do you follow me? So you should implement this in this order, this and the second, and then third, fourth, fifth, sixth, seventh, eighth, not first, second, third, fourth, and so on. Any questions? We are just reviewing. If you have questions or difficulties, ask me. And then after finding k part and L part, we do the same weight averaging for k part and L part. And yes?
Back to the 2D R4.
Mm-hmm.
When we break the second order differential equation into a system of 2 first order, and you say y double prime is equal to z prime, and then the other variable z
Is y prime.
How do we determine what z is a function of when we break up the system into k and L? I have some difficulty understanding what I am incrementing when I say y prime is equal to z.
Mm-hmm.
Okay. How do I increment z?
We don't increment z. We increment only the independent variable. Good question. Assume that we have a differential equation like this. Then I will use t very intentionally. Assume that we have a differential equation like this. Then we increment only t. So t0, t1, t2 are incremented by us. Then what about y? Y is determined. Initial value is given by the problem, but afterwards, y is determined by our method, right? Our method determines we do not know what might be the case. Same thing happens to z. In other words, z0 is given by the problem by initial conditions such as this one. So if we convert this thing to a system, then y is y prime is z. Then y of 0 is 1, z of 0 is 2. It's given by the initial value, right, condition. Initial condition is given by the problem. Then this initial condition is converted to y of 0 equals something, z of 0 is equals something. In other words, after this initial condition, we don't know what may happen. We don't increment directly. Only independent variable t is incremented by us. T is initially 0, and then 0 point anything, right? 0, 1, or anything. So we change this thing on our own, but we do not change the values of y or z anywhere. Just the method determines these things. So initial breakup happens on independent variable side, not y or z or something. Only this is determined by us. This gap is determined by us.
How did I know what the independent variable was from that first differential equation?
Generally, when you write the differential equation, then y prime equals, and then f of, unless we skip the variable, we have the first one, such as t or x, to be the independent one, and then following one, such as y or z or something, or these are dependent one, determined after calculating after finding the solution to the differential equation. So these are generally independent one that we can arbitrarily break up. But afterwards, y, z, or following things are all determined under the initial condition and the method. Any other questions? So as you can see here, initial condition is given by the problem, right? The initial conditions are given by the problem, and with this condition, we start off, and then from using y0 or x0, we can determine what? x1, right? Using x0, we can determine x1. Using y0, we can determine y1. And then using y1 or x1, we determine x2 and then y2. And then x2 is used to determine x3, y3, and so on. So only condition that is given for dependent ones are the initial conditions. Any other questions? And we can apply this to any dimensional function, right? So almost a verbatim one, but in this case, we should be careful. We should calculate the first row completely, right? And then after calculating the first row, we calculate the second row for varying case, and the third row and so on. We should not calculate K1, K2, K3, K4 for a fixed one, and then go to the next one. Then it will create an error because unknown values are plugged in inside this kind of functions. Then, as I mentioned before, when we have nth order differential equation, we cannot directly solve. So nth order differential equation cannot be directly solved. We must convert nth order differential equation into a system of first order differential equation, of a system of n first order differential equations, right? System of n first order differential equations. Then as you can see, we break up this way. y0 primed is y1, y1 primed is y2, and then yn primed is called, I defined it here, right? So it's defined here. y0 is y, y1 is y0 primed, y2 is y1 primed, and so on. All definition. Because under this definition, we derive this kind of relation. This portion is just the definition part, right? This portion is definition part, and then this portion comes from the differential equation itself. And then initial conditions are given by the problem. So initial conditions are given by the problem. Any questions? So when you have first order differential equation, I will write it. When you have a first order differential equation, then we have a differential equation like this, and then a y of 0 equals, for instance, 5. This is given by the, right? So this is first. When you have second order differential equation, like this, then y of 0 is, for instance, 5. Y prime of 0 is 2. So these should be given. These should be given by the by the way, when you solve the homework problems, you will encounter the huge increase in function in some method, then you don't have to find it from 0 to 1. You may stop when function grows too fast. For instance, I will let you know. For instance, if function is defined between 0 and something, and then you want to find the value from 0 to 1, but somehow, if the differential equation has some kind of like pole style thing or denominator equal to 0 style thing, then we cannot achieve the goal. Do you know what I mean? We want to find the solution from 0 to 1. But sometimes the function blows up before it reaches the goal, right? Reach the destination, it may blow up. Then your solution should stop before this singular point, right? Do you follow me? So when you solve differential equations, you should not go all the way to the end. You may stop when the value blows up. For instance, at 0.94, the value goes to infinity, then you don't have to find values after this. You just stop around here. Do you follow me? Whenever the solution blows up, then you don't have to go any further. You just stop at some point instead of continuing. Because once it blows up, mathematically, it is impossible to find the correct one afterwards. Why does this kind of thing happen? Because when you have nonlinear equations, when you have nonlinear differential equations, this can happen. When you have linear equations, we can predict. Depending on the domain, we can predict this kind of thing. But when you have nonlinear equations, then this kind of thing can easily happen without our recognition. So whenever you create your algorithm to solve differential equations, then you should create some kind of checking part. In other words, if the value of y is like over like 1 million, then you may refine and then check whether it is a point like this one or not. And if it's a point like this, then you don't have to go any further. Just you can start like at 0.9 or, and it's your choice, 0.91 or 93, you may stop, right? Because its meaning is after this. Do you follow me? So solving differential equations means we need to know a little bit about the theory of differential equations, but not very much. Especially this part, singularity may happen when you handle nonlinear differential equations. Linear equations we can predict, but nonlinear we cannot predict. Any questions? In any case, we covered straightforward method, and because RK4 is very nice, almost everywhere you can use RK4. But we want to learn more, because if we somehow develop tools for a company, then we don't have to do any more research. Just use RK4 all the time. That's enough, because you don't want to waste time. But we want to learn possible improvements, right? So how can you improve the method? Then, as I mentioned before, the idea is this. Currently, we are handling explicit method. we know the height here, and using the known heights, we guess or we find the unknown heights. So called exact method. So up to this point, we handled exact method. Using known one, we determine unknown one. But possible improvement can happen when we use unknown result as input, right? If in exact method, this one is output. It cannot be an input, right, in exact method. But in implicit method, this itself can be both input and output, right? This can be both input and output. Then how can this happen? We can predict by using exact method, predict the approximate height by some exact method, such as RK4 or Euler. So using some exact method, we predict. And then using the formula requiring this as both input and output, we correct. If we correct just one time, it may not be very accurate, so we correct many times. So we create a loop. So this is predictor-corrector method. So this is a possible improvement. But I investigate both cases, but still RK4 is better in many cases. RK4 is better. But when the differential equation type is very strange, then RK4 may not work well. Then we need to use something.
You do the predicting using either Euler or RK4. Is there any difference in accuracy, number of
If input is better, then output could be better. That means it can converge faster. In other words, using RK4 to predict might be the best choice because RK4 is dominant. There is no other reason to avoid, right? Avoid RK4. So RK4 can be predicted for all possible problems. But someone may think it's overkill because just Euler might predict, and then corrector may do the job of RK4. But it doesn't matter. We are not developing tools. We are just learning possibility and the possible improvement. And another way of doing it is using, instead of uniform T0, T1, T2 space, we may use different style spacing, right? For instance, very famous one of this type is Chebyshev. What Chebyshev did was this one. Chebyshev considered the circle, but I will not sketch the whole circle, just portion of circle. And then he evenly divided the circle following the arc, right? Following this. And then he just projected down. Then we can get the interval, right? We can get the interval. So what he did was creating this kind of interval. And in some cases, this kind of thing better interpolates the polynomial or better interpolates the solution. So this is unevenly divided space. But people are trying many, many things to improve. But as I mentioned before, RK4 is so dominant, people do not find much merit. But when should we use other methods will be mentioned later, especially when you cover backward difference method. And then different thing might be this. We are using just the previous result to determine the next one. In other words, y0 is used to determine y1. And then y1 is used to determine y2. And then y2 is used to determine y3. So when we determine y3, we don't care about these two heights at all. Right? Single stem method were studied up to RK4, right? Single stem method. But now we can use all these things all these things to determine the next one. Then it's called multi-step method, right? Then you may wonder, what about the beginning points? In other words, assume that we need to use 4 previous points. But in the first place, we don't have 4 previous points. Do you follow me? In the first place, we have just 1 initial value. We don't have 4 points. Then what can you do? You can mix. You can mix, or you can do anything you want to do. For instance, I will unevenly divide, or I will do this and that. In other words, I will break up, and then I will use RK4. I will use RK4 to determine these 4 previous heights. Do you follow me? So after using RK4 to determine these previous heights, then you can determine the next height, right? You can determine the next height. So this is the thing that you can do, right? To use multi-step method. Initially we use something, but if we use exact method and then use these things to calculate the next one, we may defeat the purpose, right? So in this case, sometimes people use refined intervals instead of general intervals. Do you follow me? Sometimes people use refined intervals to make these things as accurate as possible. But this kind of refinement may require some programming complication. So in my opinion, for the homework, just to use the same evenly divided space for the homework. But if you need to use multi-step method, then you may refine. For instance, generally you might divide the interval by, for instance, 0.1. Generally you do these things, and you assume that you need to use 4 previous heights. Then you may break up this more, like this kind of thing is added, this kind of thing is added, and this kind of thing is added to create these heights. So you create the heights of all these things, and after creating the heights of all these things, you use first one, and then second one, and then third one, and then fourth one in the actual multi-step beginning, right? So when you begin the multi-step method, you may use these heights, but to secure the correct heights, we may break up more in the first point. Do you follow me? These are possible approaches. But as you can see, if you do these things, then it requires more programming portions, and some kind of complication may happen, right? So it's possible, and people really do it, but you don't have to do it for the homework. Just evenly divide, and then use RK4, 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 and then after finding, you can. What else is possible? Sometimes people use weight. Even RK4 used weight. Do you remember? RK4 used 1/6, and then first slope, and then second slope, and then third slope doubled, and then, right? RK4 used these kind of 6 different slopes, right? And these are weight, right? Weight is 2 in here. So we can generalize weight, and then this kind of thing can be possible improvement. But I decided not to cover these kind of improvements, even though there are a lot developed. I decided not to, because, as I mentioned, RK4 is very nice enough to handle almost all possible cases. Then, if you don't have any more questions, I will continue to introduce the things from the, including a few cases that I covered last time. Maybe Adam's method will be the one that I want to focus. Any questions? Then let's return back to the summary. And I mentioned about improvement and implicit, multi-step, unevenly divided interval weight, a lot of possibilities. Of course, if you consider different idea, then you can develop and publish a paper. Then your paper may open the door for the new direction. In addition to these things, someone developed different improvement ideas. So predictor corrector mentioned, and all these were mentioned. Midpoint in different name is mentioned, but should never be used. This is divergent method. So the method is trapezoidal method, and it looks like Hoynes method, but there is a clear difference. Hoynes method uses explicit approach. In other words, from the previous point, we decide the next point without assuming anything. Just previous point is enough to determine the next point. It's Hoynes method. Formula looks similar, but trapezoidal is quite different. Trapezoidal method is a predicted corrector method. Like Hoynes, it predicts the height. So I will show you the difference. In Hoynes method, we use the previous height to determine the next height by using some average. But so this is Hoynes method. In trapezoidal method, initially it looks like Hoynes. But afterwards, we use the formula repeatedly to correct. So this is the similarity and difference of Hoynes and trapezoidal method. Do you follow me? So Hoynes and trapezoidal look similar in formula, but there is a clear difference. Trapezoidal is predicted corrector, meaning implicit method. And then implicit method requires looping. But Hoynes method does not require any looping, just straightforward calculation of the exact height. Any questions? Then I will save and go to the next page. The next thing is RK2 I mentioned, and RK2 is the version like this. We do not increase fully. We increase just half, right? We do not increase full H. Do you follow me? This is the RK2. So this is also called midpoint method, right? Midpoint, because it uses real midpoint. There are two different midpoints. The previous one should not be used. This one can be used. Then why do people use these things? RK4 is so dominant. What about using RK4 all the time? Sometimes you don't need exact solution, or sometimes you don't need exact solution, but you need speed. Then as you can see, to do RK4, you need to calculate K1, K2, K3, K4. But if you use RK2, then just this portion that can be called K1 is enough. Then it will speed up, right? It will speed up your program. So when speed is more important than accuracy, then you can use RK2 or even Hoynes method. Any questions? Then, now, beginning of multi-step method, I mentioned multi-step, and Adams developed the idea, and in divide difference method. I will write it. Backward difference. So these are possible multi-step method approach, and they both used interpolation. So Adams method and backward difference method both use interpolation. Then what is the difference? Similarity is using interpolation. Then what is the difference? This Adams method interpolates y prime. Backward difference method interpolates y. This is the difference. Do you follow me? So Adams method requires integration because it interpolates this thing. If you interpolate this thing to find y, you should integrate. backward difference method interpolates y. So after interpolation, to use differential equation, you should differentiate. So this is the similarity and difference. Both interpolate, but Adams interpolates y prime, backward interpolates y. So I will briefly overview both methods. We are collecting the heights, right? So we find heights. Then these heights can be interpolated, right? These heights can be interpolated. Then if these are interpolated, we can predict the next one, right? We can predict the next one. So this is the approach for both methods. But one interpolates y prime, the other interpolates y. This is the difference. And I found that the derivation may bore you, and I felt it's not a good idea to show you the details. In the past, I sometimes spent like 2 sessions to cover the proofs of these things, and I thought it's just good enough to explain the idea and then possible approach. So idea is mentioned, then possible approach is this one. Assume that you just use 2 points, right? Or if you use 3 points. So depending on the number of points, we may have different formulas. Do you follow me? Depending on the number of points, number of previous points, we may have different formulas. So you will see many different formulas. And one more thing is this one. Am I too fast, or you completely follow everything up to this point? Interpolation, y prime, y, and then how many points? Not very much, right? Then the next thing we can consider is this one. Assume that the target is this one. We want to find the height at this point. If we don't include this, in other words, if we just find heights up to this point and don't include this, then it's the explicit method, right? It's the explicit method. But if we include this kind of heights, then it's implicit method. So depending on explicit and implicit, we have different name attachment. This portion is developed by Dashboard. This portion is developed by Morton. Adams developed the general idea, but the details were developed differently. For explicit, Dashboard. For implicit, Morton. So I will begin to use the idea of these things to determine the formula, and I will briefly mention a backward difference method. Backward difference method requires differentiation in the end. It uses implicit in the first place. Backward difference uses implicit in the first place. So roughly, we are ready to handle the case, and I will begin to introduce formula. Take a look. So after this kind of calculation, and I derived first order case and second order case using long lines. But in any case, Dashboard's method is explicit method. As you can see, if we use just one previous point, then we add this portion here. This is exactly the same as Euler's method. Do you follow me? We use just previous method, then it's exactly Euler's method. But if you use two previous points, then it is B2 attachment, right? And it is B3 attachment if you use 3 previous points, 4 previous points. So theoretically, you can develop as long as you want. Assume that someone gives you a PhD and a job. If you calculate B10 or B100, would you do it? So this is the possible direction. And similarly, Morton method is developed using explicit idea. And as you can see, to calculate the height at x sub n plus 1 or t sub n plus 1, it uses the value at n plus 1 point, right? As you can see, it's implicit method. Then how can you know this value? We don't know this value. To calculate this value, we need yn plus 1. But we don't know yn plus 1. Then how can you know? We should use predictor corrector idea. We should predict by using either RK4 or Adam-Dashboard's method, we predict. After predicting it, we correct. And this means looping. Split method doesn't require looping. Just one time calculation determines the next height. Do you follow me? But this requires several time calculation, looping, right? We should loop to correct and correct and correct. Any questions? And then we can develop second or two-point UCD, three-point UCD, right? So this is uses itself. This uses previous one and itself, and this uses two previous ones and then itself, and then three previous ones and then itself. So this is called Adams-Moulton method.
Use the number of
Previous heights.
Anytime we use more, the more accurate.
There is no guarantee. There is no guarantee. Because when we include more, also error increases too.
So what's the choice?
Mostly people like about 2 or 3. Any other questions? And I showed you all possible derivations. So if you are interested in theory, not just applying the given formula, then just read through these things, ask questions next time or during office hour, or you can make an appointment with me. But in any case, for homework, you don't have to derive. You just use them correctly. You predict the height if you want to use Moulton's method, right? Predict the height and then calculate the new height and then loop. You should loop these things. Then backward differentiation also derives it, but it interpolates y. This is the difference, right? It interpolates y and then do the differentiation in the end. Do you follow me? So it interpolates y and then do the differentiation. Interpolates y and then do the differentiation in the end to make a formula. And then it looks like this. Take a look. Take a look. To calculate ym plus 1, it requires ym plus 1. So this is a typical example of implicit method. Then how can you know ym plus 1? RK4 or anything. It's up to you. And you may use 2 previous points, right? And then you 2 previous points to determine this one. And then 3 previous to determine this one, 4 previous. And I also showed you the derivation of these things. So derivation of Adams' formula and this backward differentiation may require 2 or 3 sections. In the past I did it, but I realized it's better to just explain the implementation more than just theory.
The only backward differentiation you're really doing is if k is greater than 1.
K is greater than 1 means what is the K?
And the k for backward differentiation.
Any order is possible depending on the number of previous points. Any order is possible for any method.
But the k equals 1 is not doing any pre- or backward differentiation in that case. So, I mean, from looking at the formula we have there.
But as you can see, to apply this thing, at least this is required even in 1. At least we should know this. So do you clearly see the picture? I didn't derive these things, but you now see how to apply and what case used. Why do we care about these kind of things? And theoretically, people investigate the cases. Sometimes RK4 may give us some undesirable result, especially people investigate the case called steep problem. What is steep problem? So explaining these things may take more time, but in any case, some cases cannot be solved by RK4 efficiently or accurately. Then we may need something else, right? So one typical example is some equation called steep equation. But we are not interested in differential equation theory. But as I mentioned before, higher order means good thing? No. Because it involves interpolation. Interpolation creates a Runge-Marais phenomenon. That means already the interpolation is very far off. That's the reason why I said increasing the order doesn't mean increasing the accuracy. So even if you calculate this thing for k equal to 100, nobody may give you PhD because of this reason. In any case, this is the end of the initial value problem. And I want to focus more on boundary value problem because I want to finish at least the practical part today. And then later, I may explain the reason why the formula works. In other words, if you want to know why this formula is created or that formula is created, then I can explain later. But right now, I want to focus on the practical side. So before jumping into boundary value problems, if you have any questions about initial value problem from the beginning, then ask it. But after taking the course, somehow, if someone asks you to create some numerical method to solve differential equations, forget all other things. Just remember RK4. That's all you need to do. Then they will regard you as a genius. Oh, he knows something. So no more questions? Then it's time to consider boundary value problem, and I will be very slow because up to initial value, we don't need special technique, just application of formula in different situation, right? That's all we need to know. In boundary value problem, we should be very careful. So there are two different types of differential equations, but to have boundary value, we need at least second order. If we don't have second order, then take a look. Assume that we have this kind of differential equation, then all we can provide is just one free value called initial condition. Then it cannot be a boundary value problem, or both boundary value problem and initial value problem are the same. Because of this reason, to have pure boundary value problem, at least second order differential equation should be involved, right? Then we can provide this kind of condition. Assume that we provide this thing, then it's an initial value problem, right? This is an initial value problem. But assume that we provide something, but if something is different from the previous one, then it's called the boundary value problem. Do you see the similarity and the difference? What is the similarity and what is the difference? Two numbers are provided, right? Two numbers are provided. Similarity. What is the difference? One gives the derivative value at initial time. The other gives us the value at some boundary time. So similarity and difference. This is called the boundary value problem. And boundary value problem doesn't necessarily have a solution all the time. Depending on problems, it cannot have solution. Sometimes it has solution, sometimes it doesn't. We are not studying differential equation theory here, but at least boundary value problem does not necessarily have a solution all the time. So theoretically, it's the tougher one. But roughly, this is the situation. We want to solve a differential equation. All we know is, at this point, we have this height. At this point, we have this height. This is all we know, right? This is all we know. Other than the differential equation, we have this condition. Then, the question is, the determination of this thing, right? What are the heights in between? In other words, we want to determine these kind of heights in between. So this is the thing we want to do. So generally, when you break this up by using n pieces or n subintervals, we call this height y0. We call this height yn. And y0 and yn are given, right? Assume that this height is alpha, this height is beta, then alpha and beta are given by the problem because boundary values are given. Because boundary values are given, this problem is called the boundary value problem. So alpha and beta are provided. In other words, y0, yn are known. Then the only thing that we need to determine is y1 through yn minus 1. So these are unknowns. Then what is the idea? There are about, let me check, 2. I guess 2, let me check. We will learn about 2 different methods to solve the problem. 2 different or 3 different? I guess 2 different methods. Let me check the summary. Shooting is one, and finite difference is the other. Right. We will learn about 2 different methods, and then Newton's method. But Newton's method is a general method, not just for this case. So 2 pure case plus Newton. In any case, let's not worry about the number of cases or solutions that we will study. So shooting first. Shooting is an exciting method. So take a look. We have the initial height. And the target height is already given by the problem, right? So we know both alpha and beta, meaning y0 and yn. Then shooting method is this. We convert the, I will write it. Shooting method is this. We convert the boundary value problem into initial value problem combined with bisection. This is the shooting method. So boundary value problem is solved by initial value problem with the bisection idea. This is called the shooting method. How? Initially, boundary value problem has y of 0. Y of 0 equals alpha. Y of 1 is beta, right? So these are given by the problem. But what we need is not this one. What we need is y prime of 0. Do you follow me? Y prime of 0 is not given. Then we guess, oh, let's aim at this point and then guess this thing, right? Guess this angle. So let's say, oh, I will use, for instance, 5. And then we shoot. Meaning we use RK4 to solve this initial value problem, right? 2-dimensional RK4 to solve this problem. Make a system of 2 equations, right? So we solve this system to determine the solution from this point to this point. And so after converting the boundary value problem to a initial value problem under the assumption that the y primed is 5, y primed is 5, we shoot, meaning we solve the differential equation, then we may get heights, right? By RK4, we may get these heights, right? No, it's initial value method with RK4. This portion is RK4. We use this initial condition and then apply RK4 to determine the next point exactly. Then we may arrive at some point. Do you follow me or not?
So do we know if our arrival point is good based upon our given data?
That's right.
Okay, so let's say beta is 5. We do RK4 based on our definition of 2.
Right?
We do it again with a different.
That's the reason why bisection idea is close. Right, right. It's up to you. Your epsilon can be determined by you. In any case, take a look. So we shoot it, and then we may arrive at some point. So this is the exact target, right? Given by the problem. This target is not set by me or by us. It is the target is set by the problem itself. But after solving it by exact method, RK4, we may arrive at like destination 1, right? Destination 1. If destination 1 is exactly the target, then you don't have to worry. Just stop, because you have found the solution. But this log may not happen to most people. Even if it happens, I may change the initial condition, then your program may not reach the same target anymore. In any case, this is the situation. Then if you undershoot, then you should use bigger number, right? Oh, let's say bigger number, say 6 or 7 or anything. And then reshoot, meaning resolve the problem. So in any case, you shoot and shoot and shoot, and then eventually you may go over, right? So one is undershoot, the other is overshoot, right? So after shooting many things, you will get at least one overshoot and one undershoot, right? So undershot and overshot are found. Then afterwards, you use bisection idea. Some angle gave you this kind of underachievement, right? Some angle, so I will pick on some number, right? So assume that 5 gave you undershoot and 6 gave you overshoot, right? Or 16. And 5 gave you like the value under the target. 16 gave you value over the target. Then the next angle that you can pick is what? 10.5, right? You pick the angle 10.5. Do you follow me or not? The bisection of this number, bisection of this interval. So 10.5 may be undershoot or overshoot, don't know, right? In any case, depending on this number, you pick the bisection idea. You pick the second number, and so on, and then you go to the end. And then if these angles are small enough, or if this distance is small enough, you can start. So this is called the shooting method.
2D RK4, is this a 1D problem here?
Because it's second order, you should convert the second order equation into a system of, right, first order equation. So this is called the shooting method. So essentially, theoretically, the idea is very simple. Practically, take a look. You should program this second order solving RK4, right? Second order differential equation solving RK4. It's not easy, right? Second order solving RK4. And then by applying this thing, you find the solution one time, and many times, meaning you should create a function of solving RK4 instead of individually programming it and then later returning back and reprogramming it. Do you follow me? Once the appropriate values or functions and then these initial conditions are plugged in, your routine, your function should find the solution, target D1. So it's good to create, it's not required, but it's good to create something like this. My RK4, right? My RK4 function has input such as alpha and then 5, right? So alpha 5 are plugged in, and it will give us some value such as D1 or. So this kind of function is a good idea. Then using this thing, you can find the first target height. And then once this target height is not high enough, then you can increase this number next time in the loop, not by hand, right? In your loop. So you may increase the number to 16. And then between these numbers, you can do the bisection, right? 10.5, and between these two, you can do the bisection. It is 7.75, something like this, right? So you can bisect.
So
Oh, I see. Once you hit the jackpot, so once you hit the target by using, for instance, alpha 6.98, if you use this thing, then D1 becomes the target value. Once you hit the jackpot, then that time you can present the solution of RK4 for the points other than just endpoints, right? Endpoints y0, yn are not necessary because we hit the target. Then the intermediate values that we calculated can be called and then presented as solutions. Solution is this kind of set.
What I'm saying is there more than one way to improve the end though? Could you pick a different number? So the 6.98 in this case, make that 4.
Because of the uniqueness case, if the solution is unique, it is the boundary value problem differential equation theory part. Sometimes the solution is unique, sometimes it's not. It's unique case, then we don't have to. But if it's not unique case, then we may need to find it. Any other questions? But in any case, once we reach the target, then keep this value and then rerun my RK4 to present the intermediate values. Then this is the end. So I completely explained the shooting method in abstract form. So it is very unfair. I just explained in abstract ideas. You should program all the details. It's very unfair, but what can we do? So I will pause and then you can check whether you completely understand the shooting method right. Then finally, the next method is called the finite difference method. So we have a differential equation. For instance, we have a differential equation such as this one. Right? We have a differential equation such as this one and condition. So this is a case we want to solve. Then we break up the given interval 0 to 1 and then we label these things using y0 up to yn. And then we don't know the height, so y1, y2 up to, for instance, yn minus 1 are introduced. The total n plus 1 letters are introduced, but y0 and yn are constants, right? They are not real unknowns. But for convenience, we do it. Why? When you program, it's good to have these things. Then the idea is this. We have unknowns. Exactly how many unknowns? n minus 1 unknowns, y1 through yn minus 1, right? We have n minus 1 unknowns. And idea is this. We solve something for these unknowns, right? So this is the idea. We solve something for these unknowns. So this is finite difference method. So idea-wise, it's very straightforward. We don't know the height, so heights are unknowns. Then we solve something for these unknown heights. So I will pause and then check whether you understand this highly abstract idea of solving this thing or not. So it's very highly abstract. in this form, but we will clarify these kind of things in the future. So we solve something for these unknowns is the idea of finite difference method. Then, what is this is the next question. But if you have question about other things than this one, then it's still open. You may ask the question now. If you have questions other than this part, ask. So we do not know the heights. These heights are the goal. But how can you solve for these heights is the next question, right? And what is the one that we solve? What is the equation? What is the one that we need to solve? Is the question. No problem? Or you don't understand it? So take a look. We are solving the differential equation. Solving differential equation means finding these kind of numbers. So finding these numbers is the goal. And then we do not know what these numbers are, but we use letters to placehold, right? So we placehold them. And then these are still unknown, so we should solve something for these numbers. Once we solve, then we know the height, meaning we solve the differential equation. This is the approach of finite difference. Then, now I will clarify this thing. Initially, differential equation is provided, and this is very abstract. So what we do is this thing. We break this up into localized question. We break this into localized question using finite difference. In other words, the derivative is converted to the relation between this. Second derivative is converted to the relation between these three things, and so on, right? In other words, if we consider this problem locally at this point, then is the relation between these 3 points. And then we shift. Then the problem is the problem of between these 3 points. And then the problem is between these points. And the problem is these points, and so on. And eventually, we will reach the goal. In other words, the differential equation becomes bunch of finite difference relations. This is the approach. Do you follow me or not? In abstract form, we create this kind of unknowns, and then we convert the differential equation into local problems. In local problems, derivatives and second derivatives can be converted to the relation between these 3 numbers. Do you follow me or not? In other words, we can find one relation by looking at this part and find the second problem and so on. So in other words, I will use the next column. Oh, we have enough space. So we have this problem, and then 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 this problem. So one differential equation, right? One differential equation is converted to like n minus 1, this kind of algebraic relation. This is the conversion. This part is the crucial part of applying the finite difference method in one-dimensional or in n-dimensional case. In scientific computation course, we usually cover like partial differential equations, and we solve partial differential equations using this kind of conversion in space. So if you understand this idea, then other things are very routine. But if you don't understand this idea, then ask me. So take a look. Here we had just one equation. Now we have n minus 1 algebraic relations. And these algebraic relations are mostly linear. We can add non-linear parts, but mostly linear. So we can create a system of n minus 1 equations. And we can solve the system to solve for y1 to yn minus. So this is the explanation of, abstract explanation of finite difference method. So do you clearly see the picture or not? If you clearly see the picture, others are very routine. But if you don't clearly see the picture or reason why we are considering these things, ask me. Then I will show you one example of converting the differential equation into a relation in this box. I will show you. So let's jump in. So to jump in, I will show you the conversion that you need to know. For instance, if you see y primed at the point I, then if you decide to use forward difference, then use this thing. If you decide to use central, use this thing. If you decide to use backward, use this thing. So you can pick either of these, you can pick one of these three, right? One of these three. Do you follow me? And if you need to handle the second derivative, use this thing. So you completely convert the differential equation using this chart. If you want to use this thing, use this thing. It's up to you to choose. So let's convert. So I will convert my differential equation using the chart. So take a look. Y second derivative is converted to what? This is converted to what? Y and I plus, what subscript did I use? Yi, right? I plus 1 minus 2 yi plus yi minus 1, right? So this is the conversion of this thing. And then y is yi. And then y primed is yi plus 1 minus yi over h. So take a look. Differential equation is not differential equation anymore. It's the algebraic relation of y's, right? y1 through yn. So we have a bunch of algebraic relations depending on I. So I varies from 1 through n minus 1. So how many equations of that can you have total? Y varies 1 through n minus 1 total. How many equations of that sort can you get? n minus 1 equations, right? n minus 1 relations. In other words, we have n minus 1 equations like this and n minus 1 unknowns. Then we can solve this thing. So essentially, this is it. But let's solve some actual example to clarify the steps. So I will make a simple case because if it's too complicated, then unnecessarily you suffer. So I will just solve this easy case. Y second derivative is what? And y of 0 is 1. Y of 1 is 3. So I will solve this case. And I will break up the interval. I will break up the interval from 0 to 1 by 4 pieces, 4 subintervals. So y0 is here, and then y1 is here, y2 is here, y3 is here, y4 is here. And y0 is by definition 1, y4 by definition, by given condition 3. In other words, how many unknowns should we determine? 3 unknowns. Then let's find the generic algebraic relation from the differential equation. Generic algebraic relation is this. Y second derivative is converted to h squared y I plus 1 minus 2yi plus yi minus 1, and then equals yi at generic position yi, right? I's position, right? So we created box. Box is centered at I, right? Box is centered at I. So at the center I, we create the boxes and then find the relation like this. Then let's make this simpler. How can you make this simpler? So I will arrange from lower subscript to bigger subscript, right? Smaller to bigger. So yi minus 1. And then we multiply this thing. Then But I just simplified these things. So we create the generic algebraic relation. Then it's time to center this at 1, 1, 2, 3. So I equals 1, I equals 2, I equals 3. So when I equals 1, what do we get? Y0 minus 2 plus h. H is the distance like this, right? 1/4, right? So h squared is 1/16. So 1/16 plus 2 is 33/16, right? 33/16. So I calculate this value using h. $33/16, y1 plus y2 equals 0, and same thing, y1 minus 33/16, y2 plus y3 equals 0, and then finally y2 plus minus 36/16, y3 plus y4 equals 0. Then we can chop y0, and y4 and send these things to the right side. Because y0, y4, these guys themselves, that's like unknowns, but as you can see, y0 and y4 do not belong to the left side. Left side collects the variables, right side collects numbers. So if I rewrite it, instead of rewriting it, I will just delete and then move this. So I will move this part to the right side. And I will move this to the right side. And y0 happened to be 1. y4 happened to be 3. Right? So I create this system. So the only thing that we need to do is solving this system for y1, y2, y3. So I will ask the MATLAB to calculate the result. So y1 multiplied by negative 33/16. I will keep that value. So let's call that value coefficient, right? Coefficient value is negative 33/16, right? And y1 multiplied by c with minus sign. Plus y2 Oh, I see. Yeah, thank you. So I'm a little bit, it's better to make matrix, right? C, and then 1, and then 0, right? And then 1, C, 1, and then 0, 1C. 1C, right? 1C is A matrix, right? And then B is negative 1, 0, and 3, negative 3, column vector, right? Done, right? So I save this file as, like FDM1, right? I will save this and then run it. Then these are the heights. These are the heights. So we found the heights y1, y2, y3. These are the heights. So this is the finite difference method for very simple case. And please browse the idea and ask questions. Because this portion is not very necessary, I will just copy the result and then open my file. So take a look and then check the steps and ask questions. So the key idea is converting the differential equation to algebraic relation, and after having algebraic relations for at each relation at center like yi or xi yi combination, we create n-1 equations, and we solve the system of n-1 equations to determine unknowns, heights, right? Unknown which happen to the heights. So this is the approach, and this is called the finite difference method. Because we don't have enough time right now, I will cover the general case after the break. So let's take a break until 3:05 by this clock.